People enjoy seeing images of the Earth taken from airplanes and satellites. Often the patterns inherent in these images are easier to interpret when compared to maps of the same area. An initial application of imagery for transportation planning is simply to use these data as backdrops for ancillary and map overlays, including road networks, population and demographics, and land use data in textual, graphical, and chart format. This initial application offers the first step, albeit a simplistic one, of integrating imagery data into transportation planning applications. Two key issues associated with integrating imagery into an existing GIS are data projection and image geometric accuracy. Our intent in this video is to show the ease in which imagery can be integrated into an existing GIS environment. Once integrated into a GIS environment, imagery is potentially available to everyone at the desktop level, either through an internal network or through guidebooks, reference documents, and publications. Before and after images of the Mount St. Helens volcano provides a striking illustration of the visual power of imagery. This is a color infrared Landsat multispectral scanner image of the Mount St. Helens area in the late 1970s. Resolution is approximately 80 meters. In this image, healthy vegetation is depicted in shades of red, and the cone of the volcano in the lower right quadrant and having little vegetation shows as a gray-blue. After the volcanic eruption in 1980, the area looks much different in Landsat multispectral scanner imagery. The healthy red vegetation has been displaced by reddish-brown areas, likely due to the ashfall from the volcano. The cone of the volcano is a non-distinct area, with a large blue surface area consisting of volcanic ash, mud debris, and the caldera surface. The final still image in this sequence shows that imagery is, in addition to a visual medium, a very powerful analytical data source. The various colors in this image have been created through a data processing technique known as image classification. Each of the colors in the image depicts different surface material types. For example, red depicts the caldera surface, yellow is mud debris flow, and blue is blowdown trees. Imagery analysis has transformed the original after-event image from one of only a pretty picture to one that provides a backdrop for operations and analysis. Imagery can be used to support decision-making through three-dimensional visualization techniques. Three-dimensional land surfaces can be created by co-registering imagery of an area to a terrain model formed by digital elevation model data from sources such as the U.S. Geological Survey. This example illustrates the use of three-dimensional visualization in a NASA-developed flyover of the Mount St. Helens area. Imagery is one of many possible data sources that supports transportation planning. Historically, transportation planners have relied on census demographics, travel surveys, and more recently on data within geographic information systems. Temporal trend data can be illustrated using multiple years of data. This short sequence of images shows Woods and Pool county level total employment in the Washington, D.C. area from 1970 to 2000, and then forecasted trends from 2000 to 2010. Tan and brown colors represent areas with less employment, and light blue and blue colors represent areas with more employment. Though we don't have exact statistics, transportation planning agencies historically have not been strong users of imagery. A 1994 survey taken by the National Association of Regional Councils shows that nearly 60% of metropolitan planning organizations that responded to the survey had had an operational geographic information system at that time for at least a year. The survey did not ask any questions regarding the use of imagery, but 2% of the responding MPOs used image processing software. It is likely that many more planning agencies now use geographic information systems and imagery, but barriers to the use of imagery remain, including cost of the data and finite funding, lack of available technical staff to process and analyze the data, and lack of information on the applications of imagery in transportation planning. When ordering imagery from a data vendor, you can often specify the format of the data, its projection, as well as its datum. This provides the first line of data integration into your GIS environment. If ordered carefully, and if the data are of high quality and accuracy, the imagery should integrate seamlessly into your existing data environment. When ordering imagery, you can also specify the level of geometric processing performed on the imagery after being collected by aircraft or satellite camera. All imagery data have some inherent data distortion as a result of camera orientation and terrain. Each of these image abnormalities can be modeled and corrected through post-collection processing. The standard form of post-processing results in orthophotography, in which distances and angles in the imagery are true and correct with respect to those features that are being imaged on the ground surface. The U.S. Geological Survey has published the National Mapping Program standards to provide a basis for imagery accuracy and quality. Digital orthophoto quadrangles and digital orthophoto quarter quadrangles must meet horizontal national map accuracy standards at 1 to 24,000 and 1 to 12,000 scale respectively. Projections are a mathematical means of transferring information from the Earth's three-dimensional curved surface to a two-dimensional medium. Spheroids and datums are used to describe the ellipsoidal shape of the Earth. Each is important in preparing your image data for integration into your GIS. Data within a GIS are referenced either to geographic coordinates or to a projection, such as UTM or state plane. Most agencies have a standard geographic reference system in which all of its data is referenced. In this video, we show an example using a projection known as Universal Transverse Mercator, or UTM. Image software packages allow the image analyst a means to reproject image data into different projections and datums. The reprojection dialog requests specific information necessary to transform and resample your imagery from one projection and datum to another projection, datum, and pixel sample distance. Once this information is entered, select the resample icon to choose a file name and to launch the reprojection process. It is likely that imagery will occasionally have to be registered to your base map, or that your map data may need to be registered to your imagery. This decision on which to register will take some time and must be approached with caution, since it could result in re-registration or reprojection of all of your existing data. The process of registration is similar both for imagery that needs minor geometric correction and for imagery in scanned images with no prior digital geographic reference information. In this example, we illustrate the registration of a scanned map to imagery with geographic control. Registration involves selecting and identifying control points that can be identified on both input and reference images. When all control points are selected and when acceptable registration accuracy is achieved, you must perform an image resampling, which results in a new image that has been geometrically shifted based on the offsets noted in the control point selections. This image resampling creates an image with new digital values based on a sampling technique such as nearest neighbor or cubic convolution. Once your imagery has been registered, you can use an image blend tool to visually view the image correspondence between the two images. This video has presented two issues associated with integrating imagery into the transportation planning process. We have discussed the concepts of projection and registration. Each of these concepts is critical in preparing your imagery to use as a backdrop for planning applications. Imagery may need to be projected to match data within your existing GIS as a first step in integrating imagery into the transportation planning process. Imagery will likely need to be processed to account for distortion effects due to camera orientation and terrain in a process known as orthorectification. The resulting orthophotography is highly accurate imagery data that can be integrated into an existing GIS. Imagery may need to be registered to existing GIS data to minimize remaining differences with data currently existing in your GIS. Alternatively, portions of your existing GIS data may need to be registered to imagery that has been determined to be of high geometric accuracy and quality.